All right, folks, sorry for the interruption there. I was moving my camera to realize that I was a bit backlit, and I wanted to get to a spot where you could see me better, and then I realized I had actually been stopping the video rather than pausing the video. So I'm afraid you're going to be getting this lecture in a couple of different chunks. I'll put them part one, part two, etc., so that you know the order in which to watch things. And I forgot to say so early on, I also realized, but since I'm going to be giving you a lot of names and dates throughout this discussion, it's probably in your best interests to have my handouts related to all of this that's available on Blackboard, handout on the Newtonian Revolution, in front of you and available for reference while you are watching this. Now, picking up with Hohens. So he's going to have a very diverse range of interests. Hohens is an extremely gifted mathematician and physicist, and in a lot of ways, he is the man who could have been Isaac Newton had things worked out a little bit differently. And I say this because Hohens arrived at many of the same ideas that Newton did, in some cases before Newton did. For example, Hohens was working on the fundamental mathematics of motion at the same basic time as Newton. He was studying phenomena of acceleration, and along the way, he discovered the principle we know as centrifugal force. Now, those of you who are acquainted with physics know about the clear relationship that we can see between acceleration, centrifugal force, and this thing called gravity. And Hohens was creeping towards that in his ideas. He actually formulated Newton's second law of motion well before Newton did. However, he did so in a much clunkier quadratic form. Newton would later simplify and generalize the law in a way that Hohens did not. But Hohens had certainly arrived at those basic principles. And along the way, he calculated equations for centrifugal force, which, again, you folks who know the math and physics behind this realize that between these two things, he was getting really, really close to gravitation. Indeed, his journals suggest that he was aware that something like gravity must be a force at work. And he actually rejected his own mathematics on the matter. The reason being because at a paradigmatic level, Hohens was unable to accept the idea that forces could somehow travel across empty space without any medium to carry them. His equations for gravity suggested that was exactly what was happening. He didn't think there was any possible way a force could be conveyed through nothingness, and as a result, he simply didn't accept that this was what was going on. He figured there must be something he was missing. But for that paradigmatic limitation, Hohens would in all probability be the name we would know today as the author of the law of universal gravitation. He had a wide range of other interests as well. Other scholars noted Hohens for his extremely precise methodologies, for his dedication to trying to measure things as clearly and neatly as possible. To that end, he actually designed a number of instruments for purposes of helping his science, specifically timekeeping instruments to make it easier for him to track celestial phenomena and physical phenomena. To that end, Hohens invented two tools that we take very much for granted: the pocket watch and the pendulum clock. Timekeeping, you have to understand, was up until this point in time a very imprecise science. That clocks existed, but they were rare, they were clunky, and they were very difficult to keep going with any degree of precision without constant adjustments. Indeed, much timekeeping was still handled by individuals called horologists, Horologist, who were basically specialized professional timekeepers, relying primarily on celestial phenomena to track the passage of time. Hohens was not satisfied with his lack of precision, and so he invented a pendulum-driven clock in order to use physical principles, building on Galileo's theories of pendulum motion, in order to build a more precise timekeeping tool. But the pendulum clock was insufficient for some of the work he wanted to do because it rapidly became imprecise whenever he was taking it on board a ship, and he wanted to go out on ships to take astronomical observations away from the light of cities. To that end, he invented a spring-balanced pocket watch to act as a more effective, long-distance, and more portable form of timekeeping. Hohens didn't imagine that these two tools would change the world far beyond science. For him, they were basically tools to make astronomy easier, but they ended up becoming the beginnings of a monochronic society, largely governed by marching the passage of time under specific increments. So in that way, Hohens wrought a tremendous change in society itself. I should point out that there is some dispute over the invention of both of these things. You might recall that I told you all a few weeks ago that Galileo, in his last days when he was under house arrest, designed the blueprint for a pendulum clock. But it's not clear if he ever constructed it, and Hohens certainly was not aware of Galileo's design. Likewise, the pocket watch was an instrument that was not just invented by Hohens. A scientist we'll talk about a little bit later in this lesson by the name of Robert Hooke also invented a spring-balanced pocket watch in the late 17th century. We're not actually clear, well, we weren't for a long time, I should say, which of these men invented the thing first, and both of them claimed priority. There was a certain amount of dispute between them over who was the first to invent the pocket watch. Modern science historians, having studied both men's research journals, currently believe that Hooke probably actually invented the pocket watch a couple of months before Hohens, but it does appear that both of them, working independently, came to pretty much the same idea at about the same time, and I think it's fair to give them both credit. As for other things that Hohens was doing, his study of astronomy, which was the impetus for his timekeeping, was also going to lead him to make improvements in telescopes. He tried to improve on Galileo's telescope, specifically trying to eliminate the phenomenon of chromatic aberration, the little colored rings that appear around the edge of lenses. We'll talk more about that in a little bit here because it becomes quite important. And in the course of his telescopic work, he made some important minor astronomical discoveries. Among other things, we credit Hohens with being the first to describe the rings of Saturn in detail and to discover the moon Titan orbiting Saturn, as well as the Orion Nebula. Now, you can't play around with telescopes and timekeeping for terribly long without starting to ask some fundamental questions about a long-standing problem, the speed of light. We've seen that more than one scholar throughout history, including both Ibn al-Haytham in the Abbasid Caliphate and Galileo in Florence, had tried to measure the speed of light and determined that they lacked the precision to do so. Well, Hohens is going to endeavor to do exactly that. He partners up with a Danish physicist by the name of Ole Romer, and they begin devising experiments to endeavor to measure the speed of light. Realizing that the speed changes as you pass it through different media, that light slows down as you pass it through glass or oil or water, they realized that they could build experiments using the refractive index of those materials and Descartes' laws of refraction in order to attempt to estimate what the speed of light was. Thus it was that in 1691, Hohens published a book entitled Traité de la Lumière, from the French, Treatise on Light, published in French rather than in Latin. And in this text, he describes the results of his and Romer's experiments with light. Hohens posits the idea that light is going to behave as a wave. It's the first wave theory of light, in which he describes light as having a push-pull action. That's how he looks at it in terms of how it operates, although his wave theory will eventually be dismissed and replaced by a more accurate wave theory in the 19th century. But Hohens also is going to talk in here about the results of those speed of light experiments. He and Romer ultimately conclude that the speed of light, as measured in modern units, is approximately 298,000 kilometers per second. It's actually really close to accurate. We usually round off to 3.0 times 10 to the 8th meters per second today. In reality, the actual more precise measurement of the speed of light, as understood now, is about 299,792 kilometers per second. So all things considered, given the paucity of equipment available to them in the late 1600s, Hohens and Romer came within about 1% of the accepted modern value of the speed of light. Not too shabby. One other little fun bit about Hohens, towards the end of his life, he began thinking about what it was like on other worlds. He is the first scientist we know of to suggest the possibility of life on other planets, and indeed imagine that life on other worlds must be something like life here. So he imagines that other planets quite possibly have people or animals or other things on them similar to what we have here. So not exactly talking about little gray men or little green men like we think of it now, but he's certainly acknowledging the possibility that Earth is not the only world and that life might exist in some form elsewhere that we can better understand. Hohens ends up getting rather sick towards the end of his life. He meets up with Isaac Newton for the first time in 1691. The two of them have some conversations about their mutual work on gravitation. But by that time, Newton has already published and become famous for the matter, and Hohens doesn't live much longer. He dies of his chronic respiratory illness in 1695. Now, Hohens is kind of an unsung hero in the history of science. He's one of these figures that does a lot of really important foundational work. He gives us very basic tools to work with, and he is working on a lot of the very crucial physics problems before Isaac Newton gets to them. Now, Newton is going to absorb a lot of Hohens' work. He's going to fold a lot of it into his own work without really giving Hohens proper credit. To our knowledge, Hohens never expressed any displeasure over this or even was necessarily aware that Newton seemed to be lifting ideas from him. And given that the two men were in correspondence, it's not even 100% fair to say that Newton was just plagiarizing from Hohens. They were both attacking similar problems. They attacked them from slightly mathematically different angles. But Hohens was certainly informing the conversation. He was contributing to this overall discussion in the physics of the day about how things like gravity and light and motion are going to work. Now, let's get into some place where we have a little bit more of an explicit conflict between scholars, which we're starting to see the politics of the history of science really creeping up. Let's talk about a German polymath by the name of Gottfried Wilhelm Leibniz. Really good German name right there. Leibniz was born in 1646, died in 1716. Polymath scholar of very diverse accomplishments at various points in his life. Leibniz could have been referred to as an essayist, a diplomat, a political theorist, a mathematician, a physicist, even an alchemist. He was accomplished in an incredibly diverse range of subjects. Leibniz was going to contribute to virtually all areas of scholarship in his day. There has to this day never been a full accounting of all of his writings. He didn't actually publish all that much. Leibniz published 2 full books in the course of his career and a wide variety of articles and pamphlets. But a lot of his ideas are found in more than 15,000 known letters that he exchanged with other physicists, mathematicians, and scholars throughout Europe. And nobody has ever gathered together all of that work in one place and put together a comprehensive listing of all of his ideas and achievements. Leibniz was born into great wealth. His father was a professor at the university that bears the family name, University of Leibniz. Quite precocious, taught himself Latin by the time he was 12 years old, entered university when he was only 14. He spent his life in the patronage of various nobles. He was multilingual and quite gifted as a legal scholar, and therefore often found good employ as a diplomat in the politics of the many small principalities and duchies that make up what is today the nation of Germany. Leibniz gained a reputation as a shrewd negotiator and a somewhat ruthless diplomat, but one who was a good person to call upon. But science was also a thing he pursued, and eventually he left the diplomatic life to take a salaried position as an alchemist in the city of Nuremberg, where in addition to alchemical work, he also pursued his own research into physics and mathematics. Gottfried Leibniz's achievements are quite considerable, and if you've studied math, you might already be aware of some of the things he contributed. Among other things, Leibniz gave us what is today known as Boolean algebra. He invented the binary system, which of course is the basis of computer science. He devised the notion of the algebraic function, the fx formulation that all of you are familiar with. Pardon me. He devised symbolic logic, did some important work in the field of topology, and was the first person to use a linear matrix, what's sometimes called Gaussian elimination today. In the realm of pure physics, Leibniz anticipated the work of a much later fellow named Albert Einstein in devising a basic theory of relativity, although he did not mathematically back it up the way that Einstein was going to become famous for doing. Leibniz would propose that space, time, and motion are all relative to the observer. He's also going to propose an early version of the law of conservation of energy, which he calls vis viva, which is sort of a rival view to Isaac Newton's law of conservation of momentum. He's going to suggest that, a difference between the conscious and the unconscious mind, making him one of the first thinkers in the realm of psychology. In the realm of geology, he's going to be the first person to suggest that the Earth has a molten core, and that it's from that molten core that lava arises in volcanic eruptions. He's a huge advocate of applied science and is a big fan of using alchemy and physics to build devices and inventions of use to human society. He invents the first practical desalination technology, although it's nowhere near as efficient as anything we can do today. And he actually builds a simple steam engine, although his steam engine is not terribly efficient at all. It's not useful to do any meaningful work. It's more a demonstration of principles than anything else. Leibniz is a big advocate for scientific societies. He thinks that scientists do their best work when they come together. And he's the founder of the Berlin Academy of Sciences in the year 1700, an organization which still exists today. Now, if you know the name Gottfried Leibniz before today, you almost certainly know it for his single biggest and most controversial contribution, and that is calculus. Now, the need for a mathematical toolkit that can do the things that calculus can do was quite obvious to mathematicians by the mid-1600s. And pretty much anybody who was anybody in the mathematical community of Europe was trying to work out calculus at that time. We knew that we needed some way of studying changing systems in that way. It was becoming increasingly important for the growing fields of physics and astronomy. And mathematicians were racing to try to work out a comprehensive system. Lots of folks were working on it. Isaac Newton was working on it. The architect Christopher Wren, who rebuilt most of the city of London after the Great Fire, was working on it. The Flemish mathematician Nicolas Fatio was working on it. Leibniz was working on it. A lot of people were trying to build calculus at this time. They pretty much all knew about each other, and most of them were actually in correspondence with one another. So in archives that contain their letters, we're able to follow their research quite well and to get a picture of who was working on what ideas when and what they were saying to other mathematicians about it. So at one and the same time, there was competition over this, but there was also collaboration. Now, let's build our story here. Newton and Leibniz are the names that you hear most commonly associated with the development of calculus. Depending on what math textbook you read, you might find it attributed to Leibniz, to Newton, or to both men. Let's make a case. Gottfried Leibniz kept very detailed journals of his work. We know that he began his calculus research in detail in the year 1674. We know he made a big breakthrough in 1675, worked on the project for approximately the next 9 years, published the first paper making use of calculus principles in 1684, and put out his full calculus text in the year 1696. Now let's look at Isaac Newton. Newton is not going to publish anything using calculus until a partial version of his system, which he calls fluxions, F-L-U-X-I-O-N-S. He publishes his first paper using fluxions in 1693. He does not publish his full system of calculus until he includes it as an appendix to his book Optics in 1704. The Principia is not proven using calculus principles, at least not in the published version, because Newton felt that they were not well accepted at that time and that they were not well formulated at that time. And therefore, he opted to prove everything in the Principia algebraically, which was much more clunky and complicated than doing it with calculus. But if you look at those dates, it seems like this is a pretty clear-cut situation. That Leibniz published both partial and full versions of his system well before Isaac Newton. But here's where things start to get complicated, because Newton is going to make the claim that he began his calculus research way back in the year 1666. Furthermore, he is going to assert that in 1676, when Leibniz made a visit to London and the two men were comparing notes, that Leibniz had access to Newton's unpublished calculus manuscripts. And Newton is going to begin circulating the idea that Gottfried Leibniz plagiarized calculus from him. How true is this? Hard to say. We know for a fact that Leibniz did visit London in 1676. We know that he talked to Newton at that time. We know that they visited together, that they spent a few days working on common mathematical work together. We know the two men had a lengthy correspondence about math research. In particular, they worked together on power series. So there's a lot going on that clearly they share in common. There's a lot of work with this that they've done either together or aware of each other's research. As to whether or not Leibniz stole ideas from Newton in 1676, that's anybody's guess. Newton's claiming it happened. Leibniz is certainly going to maintain that it did not. Moreover, Isaac Newton's claim that he began research on calculus in 1666, long before Leibniz, has not been an easy one to substantiate. Newton's own writings and journals from that time show that he was working on a number of mathematical problems, but not that he had made any significant progress to or breakthroughs in the field of calculus. But here's how it's going to end up playing out. Leibniz publishes his full calculus text in the year 1696. Now, in 1699, an anonymous review of Leibniz's work makes the accusation that he was in fact plagiarizing from Newton. We're not 100% sure who wrote that review. Some of the blame has been attributed possibly to a Flemish mathematician by the name of Nicolas Fatio, who certainly had cause to be in Newton's corner. The two men were very close and quite likely were lovers. Now, Newton is going to publish his version of calculus in 1704. The next year, an anonymous review of that is going to compare it to Leibniz's calculus and suggest that Newton had stolen techniques from him. We have no real idea who published that review. Now, it takes a while in the slow communities of travel across Europe in the early 1700s when everything is letters carried by ships and so forth, and especially with Leibniz moving around in the course of his diplomatic work. It takes a while for him to get wind of the fact that he is being accused of plagiarism. But throughout the early 1700s, Newton is slowly but surely spreading the idea in mathematical and scientific circles that Leibniz had plagiarized calculus from him. By the time word of it reaches Leibniz, the idea is already well ensconced. And in 1710, Leibniz first gets word of all this and is infuriated. In 1711, he goes to the Royal Society of London, which by this time is a well-established authority in these matters, and demands that they make an accounting of all of this, that they research the matter and issue a ruling on who deserved priority in the discovery of calculus. After all, they were an authoritative body. Leibniz expected that he might be able to get a fair ruling. Unfortunately for Gottfried Leibniz, the newly elected president of the Royal Society of London in 1711 was Sir Isaac Newton. You can probably see where this is going. Newton's commission to investigate the matter took no testimony or evidence from Leibniz or any of his boosters, only talked to Newton and to his supporters in England. The following year, the results of the study were issued. Newton himself secretly wrote the final finding, and surprise, surprise, determined that Gottfried Leibniz had plagiarized from him. Leibniz was pretty much a ruined man. The Royal Society of London, the preeminent scientific body in the world in the early 1700s, had branded him a thief of ideas. From that point on, he had extreme difficulty getting any kind of contracts or commissions. A lot of the nobles who had patronized him in the past no longer wanted anything to do with him. And in 1715, Leibniz died a penniless and broken man. Indeed, no heads of state for whom he had done important diplomatic work even attended his funeral, and his grave was unmarked for a good 50 years. So, who invented calculus? Most science and math historians looking at the evidence today will say, looking at Newton versus Leibniz, that the answer is both of them. That both men made vital contributions, that both men were working on many of the same ideas independently, and indeed many of the same ideas together. To ignore either of their accomplishments in this regard would be probably, frankly, a little bit unreasonable. I will say this, however. If we're looking in terms of the kind of calculus we're doing today, the notation system that we employ now is the system devised by Leibniz, not the one devised by Newton. And if we're looking strictly at the dates of publication in terms of priority, Leibniz clearly is the winner. But like so many scientific enterprises, this is the work of more than one person. Only in this case, it's showing us what happens when those people are at loggerheads. And Newton was fully willing to demolish Gottfried Leibniz's career if it was going to advance his own ideas in the matter. And this is going to become typical. We're going to find that Newton, although he is indeed working on many of the same ideas as other folks, is not really willing to share credit. And he is quite happy to leverage his political influence within the Royal Society and his reputation among other scholars in order to get what he wants and to ensure that no matter who was contributing to these ideas, that Newton's name was the one you remember. This is a pattern we're going to see coming up again and again. Speaking of, when we're talking about people who are wronged by Isaac Newton, I think that there is no better candidate than another polymath scholar, an Englishman that you might have heard of, and if you haven't, you should have, by the name of Robert Hooke. Robert Hooke was born in 1635, died in 1703. He was a native of the Isle of Wight, one of the many small Channel Islands located in the English Channel. He was a polymath scholar of incredibly diverse interests, an architect, a mathematician, an engineer, an astronomer, a physicist. Like Leibniz, Hooke contributed to virtually every area of scholarship in his lifetime, and sadly got recognition for almost none of them. In many ways, he was the Leonardo da Vinci of his era, a man who was broadly gifted in many, many subjects and was doing foundational work for other people that often went unrecognized. Now, when Hooke was born, he was not expected to live for long. He was born extremely premature. He was small. He had a severe spinal curvature. Hunchback by modern description. And it was believed that he would probably die young. In fact, his family made no provisions to fund his education beyond the age of 10, because it was expected they wouldn't need to do that. But Hooke survived, proved to be quite intelligent, largely educated at home, but his family was unable to afford a good university education for him. He was originally apprenticed to a painter, and in fact had quite artistic gifts in addition to his scientific ones. But ultimately, he ended up not being able to continue in that work. Hooke had a weak constitution, like so many of the scholars we talked about. He was sickly throughout his entire life, particularly prone to respiratory ailments due to his spinal curvature. And the smell of the fumes used by solvents in paint at the time gave him severe migraines. So ultimately, he abandoned that line of work. He made his way to Oxford, where he got employment as a chorister, working at Oxford University. In the community of the university, he met a fellow that you already know by the name of Robert Boyle. Hold on one second, folks. Okay, sorry about that. All right, anyhow, though, so Hooke meets Robert Boyle at Oxford University. Two of them bond over their common interest in science, and although neither man is exactly very healthy, Hooke is more able-bodied than Boyle and becomes his assistant in his home laboratory. The two of them collaborate on a lot of research with gases. We talked about the vacuum pump experiments that they did together last week. It is altogether likely that Robert Hooke, who was a more gifted mathematician than Boyle, is the one who actually mathematically formulated what today we know as Boyle's Law. Boyle was a good friend to Hooke, paid for him to attend classes at Oxford University, although he never actually finished a degree. And he kept him financially afloat for several years, even after his education was not quite done. This meant that Hooke was heavily involved in the Invisible College that met in Robert Boyle's home, and when said Invisible College was named the Royal Society of London in 1662, Hooke was a founding member. Indeed, he became the Royal's first curator of experiments, which meant that it was his job to not only maintain records of the experiments done by the members, but to set up experimental demonstrations for meetings of the Royal. At the peak of his career, between his own research and experiments he was setting up for other members of the Royal, Hooke was doing as many as 90 distinct scientific experiments per month. Now in 1663, King Charles is going to get wind that the curator of experiments of the Royal Society of London does not even have a college degree. And he says, well, that won't do whatsoever. But rather than kicking Hooke out, he simply issues a royal proclamation granting him a master's degree by royal fiat. Some people have to write a thesis, some people have to be friends with the king. Either way, Hooke has a degree now. He's able to secure a job at Gresham College, kept financially afloat by Robert Boyle until such time as he can, and he spends the rest of his life as a professor of geometry at Gresham, even as he does other work for the Royal on the side. Now, Hooke has an incredibly diverse range of interests and achievements. He's interested in a tremendous range of topics, both engineering, physics, chemistry, and all sorts of things. Robert Hooke, together with the architect Christopher Wren, is largely responsible for rebuilding the City of London after the Great Fire of 1666. If you've ever been to the City of London, its street grid was largely laid out by Robert Hooke in its modern form, and there are a lot of buildings still standing there that he designed. Hooke is quite interested in engineering. Among other things that he does, he works out the basic laws of elasticity. Hooke's law might be a thing some of you engineering or physics folks know. And using that law of elasticity, he builds, as I already mentioned, a spring-balanced pocket watch. His chemistry experiments lead him, along with Boyle, to the invention of the match. He does some important work in geology, among other things. Hooke is one of the first to propose the idea that landforms change over time, causing mountains to rise from flat land or erode down, causing the sea to rise and fall, and so forth. And totally independently of Nicholas Steno, Hooke concludes that fossils are the remnants of living things. He's interested in underwater exploration, and using his considerable engineering talents, builds a simple diving bell, which enables him to stay underwater in the Thames River for up to an hour at a time, making him one of the first aquatic explorers. The diving bell incidentally worked on the basis of a hand-driven pump and a hose connected to the surface that enabled someone there to keep the diving bell freshened with oxygen while you were down there. Hooke also is going to be doing some work in a few other areas. He's quite interested in meteorology. Some have called him the first empirical meteorologist. He keeps some of the first weather journals, and he invents a number of the basic tools of meteorology, including, among other things, the wind gauge, the hygroscope, and a modern form of the barometer, improving on the one built by Blaise Pascal. Now, where we know about Robert Hooke, and if you've heard the name Robert Hooke before today, it's almost certainly in the context of biology. I mentioned last time that the biological sciences really couldn't get anywhere until we had the microscope as an investigatory tool, until we had a way of looking at life at its fundamental basic units. Antony van Leeuwenhoek is often credited as being the man who got the science of microscopy off the ground. But Robert Hooke is going to write the definitive book on the subject. In 1664, at the age of 29, he is going to publish Micrographia, an English language book on the use of the microscope in science. He's going to describe the construction of microscopes and improve on van Leeuwenhoek's design in several key ways. He's going to talk about the physics behind how microscopes work, how they bend and focus light. And the book is going to be lavishly illustrated, containing diagrams of many things that Hooke looked at underneath his microscope. The structure of feathers, the wings and eyes of insects, and, most notably, pieces of wood viewed at the microscopic level. When he's looking at a slice of corkwood, Hooke notices that it appears to be divided into little boxes, one up against the other. They remind him of the chambers he had seen in architectural blueprints where monks and nuns slept in monasteries and nunneries. Those chambers are called cellulae, and for that reason, Robert Hooke coined the term cell to describe the fundamental units of life, and indeed he is the first to argue that the cell is the basic organizational unit of life. Some have called him the father of cell theory for that reason, although cell theory in its modern form was formulated by Theodor Schwann, Theodor Schleiden, and Jean-Baptiste Lamarck in the 19th century. Robert Hooke is going to be the one who's going to first establish the idea of the cell as the basis of life. Now, when you're studying microscopes and when you're looking at their physics, you're going to be learning some things about light. And Hooke is going to take note of the fact that if you put two lenses together at certain angles, that where they meet, you will see rings of colored light appearing. Those rings end up eventually being called Newton's rings. And that begins to tell you where this story is going to go. Isaac Newton is going to become aware of Robert Hooke's work with light. It's a topic that he himself is also quite interested in. And not long after reading about it, Newton is going to publish a work called De Color, on color. In De Color, published in 1669, Newton is going to talk about the refracting of light through a lens. And specifically, he's going to discuss how a beam of white light shined into a lens, or a prism, can be split into the full spectrum of the rainbow. He will further demonstrate that you can take that light, reflect it with mirrors back into another prism, and recompose it into a beam of white light. De Color is the basis of modern color theory and a fundamentally important work in optics. And Newton is going to do all this without acknowledging the priority of Robert Hooke in the matter. Hooke is less than pleased, and he is going to make public statements to the effect that Newton should probably acknowledge that maybe he's the one who discovered the splitting of light into a rainbow first. Newton is going to do the scientific equivalent of saying, well, I'm going to take my ball and go home. He's going to say, all right, well, if I'm going to have to defend my ideas all the time, I'm just going to stop doing science altogether. And he refuses to publish any new scientific work for the next several years. In fact, the Royal Society of London eventually forces the two men to make nice, and says, guys, you're making a laughingstock of all of us here. You should patch this up, and we are going to have to, we're going to have to do something about this. You're making us all look like idiots. So, yeah. Eventually, Hooke backs down. He says, you know what? It's more important that we all do good science together. That's the thing that matters here. We're going to be trying to make important progress. And that's really creditable on his part. He publishes an open letter in the London Times in which he says, hey, all right, you went further than I did with this experiment. I may have had the initial ideas, but you carried them further. The important thing is here that we all work together as men of science to make good progress in understanding the laws of nature. It was a pretty gentlemanly thing to do. Newton's going to write a letter back, also in the London Times. Newton's letter is a little bit less charitable. In that letter, he talks about Hooke's work with light, and he says, what Descartes did with light was a good idea, implying that Hooke had not made any discoveries of his own, that he was merely cribbing from René Descartes. At the end of that letter, Newton signs off with a statement you've probably all heard before. You've probably seen it across an inspirational poster somewhere, in which Newton says, if I have seen further, it is by standing on the shoulders of giants. You all know that phrase, right? If I have seen further, it is by standing on the shoulders of giants. It's probably the most famous quote by Isaac Newton. People use it to say, like, this is, acknowledging the priority of those who came before you. And the average reader, reading what Newton had written here, said, oh yeah, Mr. Newton's doing a nice thing here. He's acknowledging that Robert Hooke helped him to get to where he got to. What you don't probably know is that in the original publication, Newton emphasized the word giants. Did I mention that Robert Hooke was a dwarf? Yeah. The whole point of this letter was not to be a gentleman and acknowledge Hooke's contribution. It was a way of saying, if I got anywhere, little man, it wasn't with your help. But Hooke, in the interest of scientific progress, bit his tongue, did not respond to the obvious insult, and indeed, and this might show a little bit of naivete on his part, even resumes correspondence with Isaac Newton on topics related to motion and gravitation. And here we hit another problem. In 1674, Robert Hooke is giving a lecture about topics in physics and motion. And in that lecture, he talks about planetary movements. And he says, and let me quote directly from his lecture notes here, he says, quotes, that all bodies whatsoever that are put into a direct and simple motion will so continue to move forward in a straight line till they are by some other effectual powers deflected and bent into a motion, describing a circle, an ellipsis, or some other more compounded curved line. You physics people in here should probably recognize what I just said. Hooke is laying out here the fundamentals of both inertia, Newton's first law, and acceleration, Newton's second law, in that little talk, a talk that Sir Isaac Newton attended. 3 months later, Newton publishes a little paper called De Motu Corporum et Gyrum, in which he is incorporating these ideas. Hooke grits his teeth and keeps quiet. But the big one, the big moment, arguably, when more than any other time, Newton is going to really wrong Sir Robert Hooke, comes down to the big question of science in the 17th century, the question of gravitation. Everybody's working on it, just like everybody's working on calculus at the time. If you're interested in the science of motion, gravity is a problem you are attacking. In 1684, Robert Hooke is having lunch with a couple of other mathematicians. Christopher Wren, who's the great architect and also an interested scholar in math and physics and astronomy, and a young upcoming astronomer by the name of Edmund Halley. You probably heard that name. Well, you might have heard it mispronounced as Halley or Haley. Both of those are the wrong pronunciation. It's supposed to be Halley. He is, of course, most famous for the comet that bears his name. We'll tell his story a little bit further on in this lecture. But they're talking about their mutual work with gravitation. And during the course of that little lunch, Hooke says, I have worked out how I believe gravitation works. And he says, I believe it to be a function of the square reciprocal, which you might recognize as the inverse square law of gravitation. And he sketches out his mathematics for everybody else to see. Halley is super impressed by this. This is the coolest thing Halley's ever seen. And he's like, wow, this is so neat. And he leaves that lunch all excited about this great movement forward in gravitation. And he says, you know what? I want to show this to somebody else and see what they think. I know. I'll take it to the great Isaac Newton and see what he thinks about it. So Halley goes and visits Newton, and the two of them have a gathering with a few other folks, and we know what happened at that gathering from journal entries recorded by others who were there. And there, Halley says, hey, Mr. Newton, look at this really cool thing that's Robert Hooke came up with about gravity. What do you think? And Newton says, I've already calculated that. And Halley says, oh, really? Wow, that's great. Can I see your notes? And Newton responds by saying, you know what? I don't have them with me right now. But why don't you do me a favor? Leave that calculation of Mr. Hooke's right here, and I'll get back to you. And Hawley does that thing. And Newton cheerfully incorporates the inverse square law into his own gravitational theories. At this point, when inverse square gravitation is included in another paper that Newton publishes, and later in the Principia, without acknowledging Hooke's contribution in any way, Robert Hooke finally gets the idea that sharing ideas with Isaac Newton is probably not a good thing to do. He eschews further contact with him. The two men are very chilly to one another from that point onward. They certainly don't correspond or work together on any scientific problems from that point forward. Hooke's last years are actually rather sad. Despite his strange appearance, his short stature, his twisted back, and the fact that he apparently had two different colored eyes, Robert Hooke was apparently quite the ladies' man. He was known for having a number of prominent affairs, and most scandalously, he had a long-standing relationship with his niece, who was 31 years his junior. When she died of tuberculosis at a young age, Hooke was devastated. He went into a deep depression from which he never emerged. He himself eventually succumbed to respiratory illness in 1704. One last swipe, because Newton just couldn't resist getting it in. He'd been patiently waiting for Robert Hooke to die. The very year after Hooke passed away, Newton publishes Optics, his book on light and color, and his full theory of their actions, containing many ideas that Hooke had come up with first. Newton had patiently waited, sitting on the text for close to 30 years, for Hooke to die, so that he didn't have to compete with him and answer sharp questions about who deserved priority. In 1712, Newton's the president of the Royal Society of London, and during that time, the Royal moves its headquarters, moves out of Robert Boyle's old house after residing in it for a very, very long time, shifts to a new building of its own granted by the Crown. Whenever the Royal moves its headquarters, a lot of precious artifacts from its initial headquarters get moved along with it. Records, scientific instruments, and portraits of the founding members of the Royal. Isaac Newton personally insists on overseeing the movement of those portraits from the Royal's old headquarters to its new one. And the portrait of Robert Hooke, the only one of him that was ever done, somehow didn't make it to the other end. Presumably Newton knows what happened to it. The rest of us never will. So Robert Hooke, I think, in a lot of ways, is the fellow that's most abused by Isaac Newton, the one who, of anybody who has fallen in with working on the same things as him, he's the one that Newton most borrowed ideas from, and the one that Newton most went out of the way to insult in a lot of respects. Arguably, Hooke was his greatest competition. Now, again, it would be unfair to say that Newton was not working on these ideas as well, and as with Leibniz, we know that he and Hooke even corresponded on some of them. In fact, we have letters in which Hooke corrected misconceptions that Newton had about the work of gravity early on. But at the same time, Newton was unwilling to acknowledge that collaboration, and he certainly was not willing to acknowledge that there were ideas that other people had gotten to before he had. And he went out of his way to demolish Hooke's reputation in an effort to ensure that it stayed that way. Now, last in our hit parade of people that Isaac Newton really was competing with, let's talk about a lesser-known figure, an astronomer by the name of the Reverend John Flamsteed. Flamsteed was born in 1646, died in 1719. He was educated at Jesus College and Cambridge University. He was ordained a deacon in the Church of England. Now, Flamsteed was quite gifted as an astronomer even when he was a student. And after his graduation, he was appointed to the position of Astronomer Royal, the first royal astronomer to the English crown. In that capacity, he was given two jobs. One, he was to establish a national observatory for England, and two, he was to revise Tycho Brahe's star catalogs. By this time, better equipment was available. Let's remember that Tycho was not using telescopes. He was using open sights equipment like sextants. And so it's become increasingly clear to astronomers that although Tycho's data set really got things moving, we need to make a more precise one. And so there are a lot of folks scrambling to be the one to redo the Tychonic star catalog. Flamsteed is appointed to that position for England. He founds the Royal Greenwich Observatory, which still exists today. It's well worth visiting if you find yourself out that way in England. It's the place where Greenwich Mean Time starts, for establishing the time zones that we all know. And it was from there that Flamsteed began taking his careful and patient astronomical observations in an effort to rebuild the Tychonic catalog. He's one of several competing astronomers in different countries trying to be the ones to do this. The most notable being a German astronomer by the name of Hevelius, who is racing with Flamsteed to be the one to publish the updated catalog. Becomes kind of a nationalist pride thing. Flamsteed, trying to do it for the sake of England, and Hevelius for the sake of Bavaria. But Hevelius, fortunately for Flamsteed, is the equivalent of your old granddad who says he's not going to use one of them beeping computer things. He's got a perfectly good typewriter, thank you very much. And Hevelius refuses to use telescopes. He says if Open Sights equipment was good enough for Tycho Brahe, it's good enough for me. So he's trying to update the Tychonic star catalog with basically the same tools Tycho was employing, not making a lot of headway. Flamsteed, for his part, is happy to embrace new and improved telescopic technology, and he's making progress. But he's trying to be careful. He's taking his time. He's calculating out everything nicely and precisely. He's patiently watching the movement of planets and stars and the moon night after night. He wants this data set to be good. And along the way, he's formulating his own lunar theories as well. He's working out a theory of lunar motion. Now, lots of people are anxious for Flamsteed's data. Everybody who's doing astronomy in England wants this thing. But Flamsteed puts them off and says, be patient, hold your horses. I'm going to do it right. I will get you the updated catalog when it's ready. No one is more anxious for this data than Sir Isaac Newton. Newton pesters Flamsteed constantly, demanding that he hand over data for his own research, because Newton needs that astronomy data in his calculations of gravitation. Flamsteed occasionally will relent and release a data packet or two to Newton, but he's not happy about it. He says, this isn't finished yet, you're not going to have the best numbers, hold your horses, be patient, I'll get it to you. Newton gets increasingly insulting in his correspondence with Flamsteed. Eventually, whenever he reads about Flamsteed's lunar theory, writing him a very nasty letter telling him, hey, why don't you stop messing around with lunar theories? You're a technician. Leave the theoretization to real scientists. Just give us data. Flamsteed, in the face of that blatant insult, basically says, well, heck with you. I am not going to furnish any more data until I'm done. You're cut off. And he refuses to release any further astronomical data to Newton. Newton is infuriated. Well, eventually, this comes to a head. Edmund Halley, who had provided Newton with that gravitational formula, you might remember, was initially an apprentice to Flamsteed. He worked with him as assistant at the Royal Greenwich Observatory. But as Halley begins getting closer to Newton, his relationship with Flamsteed becomes strained, and eventually he leaves Flamsteed's service altogether, becoming a full disciple of Isaac Newton. The two men partner up on a lot of astronomy work, but they know that they're missing something. Newton, by this time, has become the personal tutor to Queen Anne and her children, and therefore he's got some pull with the royal family. And the Queen is quite interested in astronomy. Newton actually builds telescopes for her. And he goes to her and he says, hey, I really want to do more research on this topic, but that Flamsteed, he just won't give me the data. Can you maybe help out? Thus it is that in 1711, Edmund Halley presents himself at the Royal Greenwich Observatory, smugly holding forward a proclamation, a letter from Queen Anne, ordering Flamsteed to surrender his data to Halley and Newton. He doesn't have a lot of choice. He's the royal astronomer, and this is coming from the Queen herself. And Flamsteed reluctantly hands over all the data Halley and Newton had been asking for. The following year, 1712, Edmund Halley and Isaac Newton publish a joint manuscript called Historia Celestis Britannica, the British History of the Stars. This is the updated Tychonic star catalog using Flamsteed's data. Flamsteed is not acknowledged as an author or as a contributor of the data sets. Indeed, the frontispiece of this book contains a woodcut that is an image of Isaac Newton descending from heaven in a chariot pulled by swans, holding a tablet covered in astronomical calculations. Not terribly subtle. Flamsteed was so infuriated by this that he, out of his personal wealth, bought 300 of the 400 initial copies of Historia Celestis Britannica that were printed and publicly burned them in front of the Royal Greenwich Observatory. This, of course, led Newton and Hawley to say, well, look at that Flamsteed guy. Clearly, he's the crazy one here. And Flamsteed did not come out looking terribly good. And Newton and Hawley got lots of accolades for their contribution to astronomy. But Flamsteed was not done. He said, I'm still going to put together a better data set. The numbers I gave those two were not finished. They weren't ready. I'm going to do it right. And he continues consistently plugging away at his research, taking careful measurements. We actually have discovered in the course of looking at his notes today that he discovered a whole lot of new stars. And much like Galileo had done, he actually observed the planet Uranus. Didn't realize he was seeing it as a planet. He thought it was a new star. Flamsteed takes his final observations on New Year's Eve of the year 1719. Completes the last astronomical observations needed to finish his star catalog. That night, in the Royal Greenwich Observatory, he has a stroke and is found dead there the next morning. 5 days later, Edmund Hawley presents himself at the observatory to Flamsteed's widow, Margaret, and says to her, hey, I've been appointed the new Astronomer Royal now that Flamsteed is dead. Get out. And Margaret Flamsteed, who had been living there with her husband for decades, is being forced to vacate only 5 days after losing her husband. But she gets her due. Margaret Flamsteed leaves, but she takes with her every piece of astronomical equipment that is not nailed down. She sells them, and out of the proceeds, she arranges for the editing and publication of her husband's star catalog. And Flamsteed's edition of Historia Celestis Britannica is finally published in 1725. Most scholars are of the agreement that it's a far better catalog. And perhaps in one little piece of nice historic justice here, it ends up using a form of notation that Edmund Hawley introduced in the 1712 edition of Historia Celestis Britannica, a special kind of notation for describing the position of stars. But our little twist of history here that I think maybe is an ironic bit of justice is that that system of notation, although it was devised by Hawley, is today called the Flamsteed numbers. So it's something. But I've spent the last hour or so bashing good old Sir Isaac pretty hard. I've told you about Hooke, about Leibniz, about Flamsteed, about a number of people that Newton did wrong one way or another, outright stealing data from them, failing to give them credit for collaborations, insulting them, demolishing their careers in order to make sure his own work came out on top. You're probably getting a picture of Isaac Newton as a pretty nasty character, and I haven't really done a whole lot to dissuade you of that. But I feel like it's time to tell his side of the story. So, I've been talking for about an hour. I'm going to take a little break. You take a little bit of a break. And when we get back, we're going to tell Sir Isaac's side of the story. And maybe say a few words about Edmund Hawley along the way. All right? See you in a few. Hey folks, so I took a little bit of a break. Hope you all had a little bit of a break too. But let's get back to our conversation. Now, up till this point, I've been kind of laying the foundations of the Newtonian Revolution for you. We've talked about Flamsteed, Hooke, Leibniz, others who were making contributions. We've talked about Hohens. We've talked about the general attitude of the Enlightenment and the search for meaningful universal physical laws. But now I think we need to tie it all together with the story of Sir Isaac Newton himself, one of the great minds of science, one of the great influential thinkers of human history, indeed. Now, having heard everything you've heard thus far, you might be thinking, is really Isaac Newton all that special? Well, I would argue he still is. But let's tell the story of why. Now, depending on what book you read, Sir Isaac Newton was born either on December 25th, Christmas Day, of the year 1642, or January 4th, 1643. Now, this is interesting because his baptismal certificate says he was born on Christmas of 1642. But that particular year, the English government finally adopted the Gregorian calendar. The old Julian calendar that had been in use up until the time of Pope Gregory was one that the Church of England had never picked up on. The Church of England had broken away from the Catholic Church before the Gregorian calendar was adopted, and their thinking was, well, why should we bother adopting a Catholic calendar? So England remained on the Julian calendar, which was approximately 12 days off of the Gregorian calendar, while the rest of Europe was on the Gregorian calendar. Finally, that became an untenable reality. The growing international system that I was talking about made it increasingly important that the date in England be the same as the date everywhere else. So in 1642, British Parliament caved to pressure and finally agreed to adopt the Gregorian calendar. But to make it as easy as possible on commerce and the affairs of day-to-day life, they decided, in probably the most Scrooge-like move ever made by a legislative body, to abolish the Christmas holiday and make the change during the time people would normally have been off work. So everybody in England went to bed on Christmas Eve of 1642 and woke up on January 4th, 1643. But word did not necessarily get out to all of the little villages and communities all over England right away, and Isaac Newton was born in the tiny village of Lincolnshire. So nobody in his village knew that a new calendar had been adopted at the time of his birth, and that's why his baptismal certificate says 1642. A lot of people also kind of like the symmetry of the fact that he was born the year Galileo died. But, you know. So, either way, born either 1642 or 1643, depending on your calendar, died March 31st of 1727. Now, Newton's background was a lot different than many of the other scientists we've talked about. He did not come from wealth or position or power. He did not come from an influential family. His father was a farmer. He was born 3 months premature, and nobody expected him to live. The nurse who delivered him said that when he was born, he was small enough that he could fit into one of his late father's boots. I say late father because Newton's father died before his birth. Now, his mother did eventually remarry, but her new husband had relatively little interest in raising another man's son, so Isaac was sent to grow up with his grandparents, and he grew up basically in a little farming village. Now, from the time he was young, Isaac Newton was clearly brilliant and clearly very different than others. He did not enjoy the company of other kids, went off and played by himself, diverted himself with odd little experiments and amusements, invented simple machines. He actually caused a UFO scare in his village when he was about 8 years old by flying a lantern during a thunderstorm attached to a kite. He was mathematically gifted. His school teachers marveled at his ability. And from the time that he was a young man, Newton wanted to become a mathematician. Now, his family wanted nothing to do with this. His mother insisted that he was going to inherit his father's lands after the death of his stepfather, and that he was going to have to become a farmer. So they tried as a teenager to put him to work as a farmer, and it just seemed that all of his genius magically melted away whenever he was asked to do any kind of farm task. He couldn't figure out how to work a plow, he left tools out in the field during the rain, forgot to latch barn doors, all sorts of things like that. It's just he somehow couldn't manage farming. And finally, his family got the hint and was like, okay, fine, go be a mathematician. He managed this despite being a relatively poor boy because of a custom that was prevalent in English universities in the day, that promising young men, I say men because women were not yet allowed to enroll in universities, promising young men who showed academic gifts but couldn't afford a university education could get it by becoming what was called a subsizar, S-U-B-S-I-Z-A-R, sometimes just a sizar for short. And what that basically meant was that you became an indentured servant to an upper-class student, that you were attached to a wealthier, more well-to-do student than yourself, who was ahead of you academically, that you would do favors for them and do chores for them. You'd do their laundry, you'd empty their chamber pots, and all the other nasty chores that they really didn't want to do, in return for which they would pay for your education. So Newton becomes a subsizar, and that's the way that he gets through his time at Cambridge University. Now imagine for a moment, if you will, being indentured to your least favorite junior or senior from the time you were a freshman and having to do all their dirty work. Fortunately for Newton, he didn't have to do a whole lot. It happened that the student he was attached to was kind of a party animal who was never really on campus all that much, and as such, Newton didn't have a lot of chores to do on his behalf. So he was pretty much free to dedicate himself to his study, and what he really wanted to be studying more than anything else was mathematics. It's worth taking a moment to point out that Isaac Newton was, by any standard, an exceedingly odd individual. He was very blunt. He did not catch social cues. He was not really interested in interpersonal relationships. He would go on about things that interested him, whether people wanted to hear about them or not. He was extremely mathematically gifted and would shut out the entire world around him whenever he was focusing on problems related to that. He was extremely straightforward in his approach to almost everything, doing things other people might not have thought of doing. For example, when he was playing with optics, he decided to experiment on himself by taking a large, thick, blunt needle called a bodkin and prying it behind his own eyeball to distort the shape of the lens so that he could get an idea of how that changed the way that light was moving through it. Not the experiment an average person would have thought to perform. Newton was in all probability on the autism spectrum. His behavior matches the profile quite clearly, and his mathematical gifts are not unusual among people on the spectrum either. He had very few close personal ties of any kind. He was not really involved in personal relationships, never married, had no children. In all probability, he was gay. The only close personal relationship that we know of was a lengthy friendship/affair with the Flemish mathematician Nicolas Fatio. He did have some affection for one creature in the world, his cat Diamond, who hopped on his notebooks and left some paw prints on some of his journals and papers. That we know that he regarded Diamond as the most loving animal he had ever known and the only close personal tie that he enjoyed. Now, during his time at university, Newton threw himself headlong into research. By the time he finished his bachelor's degree in 1665, he had already shown himself to be a mathematical prodigy. In fact, he had already, at that point, published a paper on polynomials and discovered binomial theorem. But the year he graduated, he had to go home. Apropos enough, during the 1665 to 1667 period, London was caught up in an outbreak of bubonic plague. And so everybody had to go do their classes remotely for a little while, except they didn't do classes remotely because there was no good way to do that at the time. Everyone was basically just sent home for 2 years while the plague died down. So Newton went back to his family's farmhouse, stayed there for 2 years, and later said that the so-called plague years were the most productive time of his life, because then he could focus on doing all the math that he wanted to do without the distractions of other classes that he thought of as less important or the academic schedule. Now, the plague eventually lifted, and in 1667, Newton returned to Cambridge, where he accepted a fellowship at the university to get his master's degree, continued in that path, and got his MA in relatively short order. Having completed that, he was offered a long-term position at the university. Now, the position he was offered was the Lucasian Chair of Mathematics at Trinity College within Cambridge University. The Lucasian Chair of Mathematics is to this day probably the single most prestigious mathematical appointment in the world, It has been held by a number of luminaries. Not only Isaac Newton has held this chair, but also such people as Charles Babbage, the father of computer science, and most recently, Sir Stephen Hawking. Now, Newton was quite privileged to get this chair at such a young age. But to become a fellow at Trinity, there was a rule at the time that anyone who was a fellow at Trinity College had to be ordained as a deacon or a priest in the Church of England. Newton did not want this. Not because he was opposed to religion. Indeed, Newton was very religious, very spiritual. But his particular problem was that he was a heretic. Newton was an advocate of the old Arian heresy, which I've mentioned in here before. A-R-I-A-N, Arian heresy, or Arianism, which is the idea, if you don't recall, that God is unitary rather than trinitary. There is no separation of Father, Son, and Holy Ghost, that it's all one being. And Newton was quite clearly aware that if he became a priest, sooner or later his heretical religious views were going to come out, and that was not going to work out well for him. But he found a loophole. Digging around in the archives of the university, he discovered an old provision that stated that one of the terms of accepting the Lucasian chair was that whomsoever held that chair could not interfere in the politics of the church. Newton wrote a letter to the king saying, hey, the only way to really guarantee that I won't interfere in the politics of the church is to exempt me from the requirement to become a clergyman. The king bought this, and Newton was exempted from the requirement, and the Lucasian chair was thereafter exempted from that requirement. So he got away with concealing his unorthodox religious views and got a permanent position at Cambridge. By all accounts, Isaac Newton was not a man you would want to have as your professor. He hated teaching, didn't want anything to do with it. He saw it as a distraction from the important work of mathematical and astronomical research that he was really there to do. His students caught on to this. They didn't like him teaching them any more than he liked doing it, which meant a lot of times people never showed up for his classes. But Newton, showing the kind of stubborn mind that typified so much of his career, would give his lectures, as he was required to do anyway, to empty rooms. And thus it was that it was not a terribly unusual sight at Cambridge to pass a lecture hall and see Isaac Newton angrily lecturing to a room full of chairs. Now, when he was not having to do his professorial duty, Newton was dedicating himself wholeheartedly to mathematical research in the tradition of people like Huygens and Galileo, looking to link mathematics with physical laws and see how all of this came together. As I said, he's not unique in this regard. Most people who are doing math at the time are interested in these problems, and Newton is no exception. So he's participating in an active and lively scholarly community in which you've got plenty of folks trying to solve problems like gravity and inertia and acceleration, to work out equations for the motion of the moon and the motion of planets, building on the principles laid down by Galileo and Johannes Kepler. Copernicanism is broadly accepted by this time, but there are still holdouts, still folks who aren't so sure about it, largely because there is not a solid mathematical proof to demonstrate it. I won't say that Newton was setting out to solve Copernicanism, but he was setting out to understand the basic physical laws behind it. Tycho had offered reason to believe that the heavens and the earth might follow the same rules, and Newton wanted to pursue that much further. Now, Isaac Newton's list of accomplishments is quite significant, and you've already heard some things about it from the course of our previous discussion, woven in with other people's work. In the field of optics, Newton, regardless of whatever else Robert Hooke was doing, devised the fundamentals of color theory. He did a famous experiment inspired by Hooke's work in which he poked a pinhole in a window blind, shined a thin beam of light into a prism, split it into a full spectrum of color, and then used another prism to recompose it back into a single beam of white light. In this way, Newton demonstrated that so-called white light actually contains all the colors of the rainbow, and he offered a color theory suggesting that color was an inherent property of light rather than an inherent property of objects. Previous visual and optical theories had suggested that something emerged from our eyes, touching objects in the environment and making us aware of their inherent color. Newton realized that what was really going on here was that objects reflect certain wavelengths of light and absorb other ones. And the colors we see are the wavelengths being reflected back to our eyes, thus improving our understanding both of vision and of the behavior of light. Along the way here, Newton discovers that light always splits into a spectrum in a consistent manner. You all learned the acronym in high school or elementary school probably, Roy G. Biv, right? Newton realized the order in which the colors of light come. Didn't know why, but he knew that there was a consistent pattern to it. Now here's the thing. When you learned Roy G. Biv in elementary school, they probably taught you red, orange, yellow, green, blue, indigo, violets. Well, those of you who are physics folks are aware it's not quite that simple because indigo isn't a real color in the spectrum. Indigo is just kind of a chunk that we carved out of the violet and blue portions of the spectrum. There are really just 6 distinct colors of light, not 7. Now, the reason we have this is because Newton had a personal idea that light and sound were connected in some way, and therefore he believed that there would be 7 basic colors of light, just as there were 7 notes in a musical scale. And so Newton is looking at his rainbow of color and seeing, okay, yeah, 7 colors of lights. Red, orange, yellow, green, blue, oh crap. Indigo, violet. There we go, that's 7, right? So Newton shoehorned indigo in there to make it fit his model. And even though physics as a discipline recognizes that indigo is not a real distinct color now, we still tend to include the I in the Roy G. Biv acronym, if for no other reason that makes it a lot easier to remember when you're in 3rd grade if you've got a vowel in there. So Newton lays down some important optical principles. He ends up devising a full scheme of the science of optics, which, as previously noted, he publishes in his book Optics in 1704. He doesn't actually put that out there until after Hooke's death because he doesn't want to be arguing with Hooke about theories of light. One thing that Newton offers forth to differentiate himself from Hooke was a so-called corpuscular theory of light, in which he suggests that light follows the form of a stream of particles rather than a wave. And Newton's corpuscular theory of light is the one that's going to last for most of the 18th century, only to finally be dethroned in the early 19th century. And I know what you're thinking. Yeah, light is both a wave and a particle. Nobody in this time knows that. We'll talk about quantum mechanics much later. In the realm of astronomy, Newton makes considerable improvements on the telescope. He invents the first reflecting telescope, which is a considerable improvement over the refractive telescopes that have been used since the time of Galileo. Using that much better telescope, Newton is able to take far more precise measurements of planetary and lunar motion, providing him with valuable data that he's able to utilize in his gravitational calculations. Which, of course, brings us to the realm of pure physics, what Newton is best known for. He's going to be assembling, piece by piece, the idea of a comprehensive set of physical laws. He's in correspondence with lots of other folks who are doing this. He is working with equations laid down by his predecessors, people like Kepler and Galileo, who'd already made contributions in this regard. Now, we've seen that a lot of these basic rules were things that Newton was receiving some of from other people. Make no mistake, he was working on the same problems. In a lot of cases, he and these people were working on them together through correspondence or even through personal meetings at places like the Royal Society of London. So, Newton is one of many contributors to these physical laws. We can say with some degree of confidence that he arrived independently at principles of inertia, things that have been talked about in some form for quite some time. We can say with some degree of confidence that he was the whole author of the third law of motion. His concepts of acceleration are stitched together from ideas discovered by Hooke, Huygens, and Galileo. Newton is going to generalize those principles, and specifically, he's going to come to the realization that if you take Kepler's third law of motion and substitute it into Christian Huygens' centrifugal force formula, that you can begin to derive an inverse square law of gravitation, a principle he had already picked up, of course, from Robert Hooke. So Newton is lifting ideas from other scholars, he's synthesizing the ideas of other scholars, and he is slowly but surely pulling together a comprehensive model. I would argue Isaac Newton's greatest genius is in seeing the big picture, that he's the one who realized how all of this fits together, that he saw the connection among these disparate bits and pieces of physics that were being assembled by Huygens and Hooke and others, and says, hey, wait a minute, these principles are united. They're mathematically consistent. We can put them together into an overall system that applies to all levels of physical reality. Newton sought to test this idea with his formulation of gravitation, using Christian Huygens' very terrestrial formula for centrifugal force to derive Kepler's laws on the basis of celestial mechanics. Because if you can do that, you can distinctly show once and for all that terrestrial and celestial, got that the other way around, terrestrial and celestial follow the same rules, the same consistent physical principles. One way or another, Newton has assembled his basic ideas by April of 1686. He's got his basic work put together, partly from lifting gravitational equations from Hooke, partly from absorbing other people's ideas, and partly from his own research and systematization. He backs up all of this with algebraic equations that he himself formulates to prove how these ideas work. And he puts it all together into a singular volume, Philosophiae Naturalis Principia Mathematica, often just called the Principia Mathematica, or the Principia for short. The Principia is arguably one of the most important books in all of science. In it, Newton introduces the idea of a fundamental set of universal, mathematically provable physical laws, principles that are consistent everywhere in the universe, principles that apply to both terrestrial and celestial mechanics, and principles that are mathematically predictable in all situations. It's an absolutist view of the universe, not a relativist view of the universe. Relativity is going to be a much later concept that Newton is never going to get to. In this book, he lays out a number of principles for which he is famous. He puts down the inverse square law of gravity and uses that as the basis of his law of universal gravitation, the idea that gravity is not simply a thing that keeps planets going around the sun, but rather that gravity is a universal force, attracting every body in the universe to every other body in the universe, however slightly it might do so. He's going to offer forth the law of conservation of momentum, and indeed the concept of momentum as we understand it today, building on ideas that go all the way back to the Middle Ages. He's going to put forward, pardon me, folks, most famously, his three laws of motion. You all know Newton's three laws of motion, I am sure. Newton's first law, the law of inertia. A body in motion remains in motion, and a body at rest remains at rest unless it is modified by an unbalanced force. Second law of motion, the law of acceleration. The force of acceleration on a body is proportional to its mass and inversely proportional to its acceleration. F equals ma. And of course, the law of reciprocal action, an idea that arguably has philosophical implications as much as it does mathematical ones, that for every force exerted on a body, that body will push back with an equal and opposing force. All of these laws are backed up by equations pulled from Kepler, Huygens, Hooke, Wren, Galileo, and his own work, with nobody except himself credited, of course. And he uses these equations and shows how you can look at the mathematical principles he is talking about and connect them to the math of Galileo and the math of Kepler. Specifically, as I pointed out, that he shows how using Kepler's laws and Christian Huygens' centrifugal force equations, you can actually derive mathematically all of Kepler's laws of motion from the principle of gravitation. The Principia is a game changer. Not only are we demolishing the ancient idea of celestial and terrestrial realms being separate and distinct that goes all the way back to Aristotle. But we are establishing a set of universal principles. Newton's genius is in pointing out that these rules apply everywhere, that they are universal laws, they apply to all motion in all situations, they are mathematically something you can model, you can test, and you can demonstrate. Newton's physics serves as the basis for pretty much every hard science that comes after. It's foundational to a lot of principles in chemistry. It allows for the discovery of other forces of nature, such as electromagnetism. It basically provides all of science with the idea of universality, that scientific laws and principles are naturally explicable, understandable by human beings, mathematically and empirically consistent, and applicable to all situations. All subsequent physical science has its beginnings with the Principia. And at a paradigmatic level, this is demolishing arguably the last remaining aspect of the ancient Aristotelian way of thinking. The notion that we have separate sets of rules for separate places, and the notion that things happen because they have a purpose. Whereas Newton is showing no, motion and action are not because of objects trying to fulfill their purpose, they're because of the operation of unthinking natural laws and principles. In a lot of ways, modern science owes everything to Newton's work here. Now, he didn't get it all. There were plenty of things Newton did not understand. He did not use calculus in his work to demonstrate the validity of his ideas. He used algebra, which was a lot clunkier and a lot more difficult. Calculus would be applied to his ideas later and allow them to expand in much more important ways, partly because his calculus wasn't finished yet at this point, and partly because he was distrustful of using an unproven mathematical system to demonstrate such important ideas. He was incorrect about his theories of light. He was incorrect about the absolutist nature of the universe, but he had no toolkit for knowing about things called relativity. One of the things that Newton was most frustrated by was the inability of his model to explain how gravity moves across empty space. You might recall that's the hang-up that caught Hohems, that Hohems never got as far as a law of universal gravitation precisely because he couldn't overcome that paradigmatic limit. And so Newton doesn't either. He goes where the evidence points him, but he can't explain it. I quote from the Principia when Newton says, "I have not yet been able to discover the cause of these properties of gravity from phenomena, and I feign no hypotheses. It is enough that gravity does really exist and acts according to the laws I have explained, and that it is abundantly serving to account for all of the motion of celestial bodies. That one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one to the other, is to me so great an absurdity that I believe no man who has in philosophic matters a competent faculty of thinking could ever fall into believing it." He knew what was happening. He did not know why. And the problem with the nature of gravitation is not one he's ever going to solve. It's one, in fact, that is going to go unsolved until the early 1900s, when a fellow by the name of Albert Einstein is finally going to come up with a general theory of relativity to account for Newtonian mechanics in a relative universe. And indeed, we didn't fully work that out until 2018, which is when one of Einstein's predictions, the existence of gravity waves, was finally proven. Now, for all of this, the Principia almost wasn't published. And there's an interesting story about why. Because Newton presented it in 3 volumes to the Royal Society of London in 1686 in April. And he presented the first volume that year. The remaining 2 volumes were going to come out over the course of the next year. The Royal looks at it and says, "This is amazing. This is going to change everything. This is a remarkable work, especially from a man so young as you. He's not yet 30 years old. It's a shame we can't publish it." Because here's the thing, folks. The Royal Society of London had already blown its entire publication budget for the year 1686 on a lavishly illustrated full-color book by a man named Francis Willoughby called History of Fishes. They thought History of Fishes was going to be a big thing. It was full of colorful pictures. Everybody likes colorful pictures of fish, right? They thought the History of Fishes was going to be the biggest thing to hit science that year. Needless to say, it was not. History of Fishes did not sell. It turns out people don't care about colorful pictures of fish all that much. The Royal Society of London couldn't give away History of Fishes. For 150 years after the publication of that book, the Royal had a storeroom dedicated to unsold copies of History of Fishes. One year, when Edmund Halley was seeking his annual research stipend and the Royal was hard up for cash, instead of giving him research money for the year, they gave him 50 copies of History of Fishes. So, that particular book almost got Newton's Principia not published. In fact, Newton was so frustrated that he was ready to withdraw from science altogether. The only reason the Principia saw print is that his buddy Edmund Halley intervened on his behalf and said, hey, look, I am super rich. I will pay for the publication of your book. So Edmund Halley financed the publication of the Principia outside of the Royal's press, and the rest is history. Now, Newton published the Principia when he was not yet 30 years old. And from that point onward, he actually didn't do a lot of science. Yeah, sure, he publishes his works on calculus and optics, and he publishes a few texts on lunar theory, and he puts out that Historia Celestis Britannica that we mentioned in subsequent years. But by and large, the overwhelming majority of Isaac Newton's serious scientific and mathematical research was done by 1686, 1687. From that point onward, he pokes at projects here and there. He ties up loose ends of other things he's been working on, but he does not make a lot of significant contributions to the sciences from that point forward. He's pretty much done his big thing. So what's he doing with his time? He remains involved in the scientific community. Newton remains a prominent figure in the Royal Society of London. Eventually, of course, becomes its president and holds that office until his death. But in other areas, he's occupying himself in other ways. He has an apparent mental breakdown in the year 1693, partly a result of overwork at the university, partly a result of the ending of his friendship/romantic relationship with Nicholas Fatio over a falling out. And for a couple years, he doesn't do a whole lot of much of anything. In 1696, he is appointed to a completely different job. He becomes the warden of the Royal Mint. The Royal Mint. He's now the guy in charge of overseeing the production of legal English currency. Under his auspices, currency reforms are made in England, and Newton initiates a crackdown on counterfeiting, which he saw as about the worst thing a human being could do. In fact, Newton spearheaded a sting operation against counterfeiters in which he personally disguised himself as a criminal, went into seedy London taverns, attempted to buy counterfeit money from people who were selling it, and then sicked the guards on them. On his deathbed, Newton was asked what he thought was his greatest achievement. He did not mention the Principia, he did not mention optics, he did not mention calculus. His first thing that he said was, I sent 19 counterfeiters to the gallows. A few years later, he becomes the master of the mints, the overall head of the production of currency rather than simply the enforcer of currency law, holds that position until his death. He also serves a brief stint in Parliament. Actually, twice he serves in Parliament. He's elected to Parliament as the MP representing Cambridge from 1701 to 1702, and again from 1712 to 1714, MP, Member of Parliament. His parliamentary service is mostly behind the scenes. He gains a reputation as a backroom deal maker. In fact, the Sir Isaac Newton, the knighthood, did not come from his mathematical and scientific achievements. It came from his service in Parliament, helping out the agenda of Prime Minister Halifax. On the actual floor of Parliament, Newton was pretty much a non-entity. He did all of his famous work there behind closed doors and behind the scenes. In fact, in the entire time he was in Parliament, there is a record of him introducing exactly one motion into Parliament, and that was a motion to have the windows at the room closed because it was too drafty at the time. Towards the end of his life, Newton writes a great deal, but he's not writing too much about physics or math. Mostly what he's writing is about theology and alchemy. He writes extensive theological texts about the immanence of God in all things and about his somewhat unorthodox theology. And indeed, he includes in there the idea that there is a mathematical code embedded in the text of the King James Bible that allows the prediction of the future. Incidentally, if you're looking at Isaac Newton's predictions, the world is going to end in the year 2787. He also writes extensively about alchemy. Keeping in mind, folks, this is a time when Robert Boyle's chemistry is several decades old. Newton is one of the last people to be doing alchemy. He's a mystic. He is a strong believer in magical principles, and he firmly believes not just in the science of alchemy, but in the magical ideas that you can use it to derive the Philosopher's Stone and the elixir of life. And he pursues alchemical experimentation long after he is done pursuing other forms of more scientific experimentation. There's a wonderful book about Newton called Isaac Newton, the Last Sorcerer, in which it discusses his late life work as an alchemist. Between alchemy and biblical prophecy, Newton wrote about 4 times as many pages on mystical topics as he did on scientific and mathematical ones. Most of his work in those 2 areas, incidentally, was not translated from the Latin until just a couple of years ago. Cambridge University was a little bit embarrassed that one of its favorite sons had been delving into so much mystical claptrap at the end of his life. Towards his latter years, Newton begins getting very weird and quirky and kind of neurotic. He has a lot of strange behavioral and personality issues. It is believed that he probably was suffering from mercury poisoning as a result of frequent exposure to that metal, which he was boiling as part of his experiments to try to create the Philosopher's Stone. Spent some time as the president of the Royal. You've already heard about some of the things he did there with Leibniz and Hooke's legacies. But the last couple years of his life, he develops a serious case of gout. He's bedridden for most of the time, and he eventually succumbs to a bout of influenza at the age of 85. He's buried in Westminster Abbey, one of the relatively few people to be honored with that particular burial site. One last little note about Newton. Arguably the most famous thing that the layperson knows about him. On his deathbed, Newton's biographer was interviewing him and asking him about things that happened during his life and his accomplishments and so forth. And he was asked about gravitation. And then he told a story that he had never told before. He said that the idea for universal gravitation had come to him not from Hooke, not from other research, but way back in 1666 during the plague years when he was at home while the university was closed up. He claimed he was beginning his work in calculus at that time, and he also claimed he began his work on gravitation at that time. The story he related to the biographer was that one night he was looking out the window of his family's house, looking out over their apple orchards, and he said that he saw an apple drop from a tree at the same moment that the moon rose over the tree. And he claimed that that's what got him thinking about gravity as a truly universal force affecting all bodies. So that right there, folks, is the origin of the apple story, which inasmuch as we can tell, Isaac Newton made up whole cloth at that time as a way of justifying his priority over Robert Hooke in the question of gravitation. So Newton is leaving a complicated legacy. He is a man who did extraordinary things for science. He is a man who treated his fellow scientists very poorly. I would argue his place as one of the great brilliant minds of science is an earned one. But I think it's really, really important that we acknowledge that his story is very complicated, that there's a lot more going on than just a man sitting under a tree till an apple falls on his head, which, again, never really happened. That Newton is a complicated figure. He did some amazing things. He did some terrible things. And filing him in one column or the other as, scientific genius or scientific villain, you need to put him in both if you want to get the full story. And that's an important thing to remember throughout the rest of this class, folks. There are a lot of folks who are neither hero nor villain, but something in between. Now, to finish out our story of the Newtonian Revolution, I want to talk about one last character who's been kind of weaving through our entire tale. And that is Newton's erstwhile protege, Sir Edmund Halley. Actually, before we get to Sir Edmund Halley, I just wanted to add one little bit of trivia here. Newton, had you asked him his profession, would have called himself a philosopher. That's how he described himself throughout his career. Remember, natural philosophy is the term that is being used for science. But that's changing. Some new terminology comes into vogue around this time, and within a decade of Isaac Newton's death, a term that he had popularized in the Principia, the word scientia, is being used in lieu of natural philosophy. And so pretty soon, this thing that we've been calling natural philosophy by the early 1700s is finally starting to be referred to as science. But back to the story of Edmund Halley. Halley was born on November 8th, 1656, died on January 14th of 1742, became known during his lifetime as an astronomer, physicist, mathematician, and actually meteorologist. Was at one point a student of both Flamsteed and Newton, and of course had sort of become Newton's protege after a while. Now, Halley was native of London, born to great wealth. His father was a very successful merchant. Even though the family fortunes fell later in his life, Halley never wanted for anything. He was convinced of wanting to do science from the time he was a young man, arrived at Oxford University in personal possession of better astronomy equipment than the university itself owned. He spent his years at Oxford largely screwing around. Edmund Halley was that guy we all know, the one who never shows up for class, the one who's goofing off and partying all the time, and still shows up and does better than everybody else on the tests. Halley spent a significant amount of his time hanging out in fashionable coffee shops, drinking, and having affairs with the wives of a lot of prominent people, including a few of his professors. Now, that said, he's doing some pretty cool work in astronomy even as an undergraduate. He wrote papers on planetary orbits. He's the first person to observe the occultation of the planet Mars by the moon, and writes some papers on sunspots. He also, in the course of his observations of stars and planets, notices some discrepancies in Tycho Brahe's star charts. He writes to the royal astronomer, John Flamsteed, about his observations. Flamsteed is impressed by his work, and the two of them become friends, and eventually Flamsteed invites Halley to join him at the Royal Greenwich Observatory as his assistant. So Halley leaves Oxford, never having completed his degree, and begins to work with Flamsteed on updating the Tychonic star catalog. But Flamsteed suggests that if he really wants to make a name for himself, he needs to do better than updating an old set of star charts. Halley suggests that nobody has ever done for the sky of the southern hemisphere what Tycho did for the sky of the northern hemisphere. And Flamsteed arranges for him to do just that. Halley sets sail on a ship to St. Helena, an isolated island in the middle of the Atlantic Ocean. And during that cross-Atlantic voyage and during his time on that island, Halley takes numerous observations of the stars, collecting a large amount of data. In just 2 years' time, he has enough data assembled to put forward a preliminary set of southern star charts. Comes home and publishes them at the age of 22, is immediately hailed as the Southern Tycho for his achievements, and is named a Fellow of the Royal Society of London at the age of 22, making him arguably the youngest person to ever receive that honor. He's, of course, remember, has not even finished his bachelor's degree at this point, but he is awarded his master's degree by royal proclamation. Later, when he becomes a professor of geometry at Oxford University in 1703, they grant him an honorary doctorate, thus making him Dr. Halley without ever having finished his BA. Some people just have it easy that way. Now, Halley is going to continue a rather diverse career. He got interested in meteorology while he was crossing the Atlantic, wrote papers about monsoons, hurricanes, pardon me, and the relationship between barometric pressure and the height over sea level. He also correlates solar heat to the movement of air masses in the upper atmosphere, laying some foundations of empirical meteorology, and combining his work with the growing body of meteorological observations by Robert Hooke. Hawley is also interested in pure mathematics. He actually, as kind of a hobby, writes the first actuarial charts as an exercise in statistics, and thereby kind of gets the science of, well, I'm not sure science, but the mathematical practices of life insurance going. In 1684, he meets Isaac Newton. The two of them get to be good friends after Hawley lifts some ideas from Robert Hooke and passes them along. After that, Newton and Hawley maintain a good friendship. Little by little, Hawley becomes more and more Newton's protege and turns more and more against his old teacher Flamsteed, until at last the relationship between Flamsteed and Hawley breaks down altogether. Newton, for his part, leverages his influence to get Hawley an academic appointment, and it's not like he really wanted for work anyway. Now, of course, what Edmund Hawley is most known for is his work in astronomy, and there are a couple of big things that he contributes. He starts off by studying ancient astronomical data, going all the way back to the Middle Ages. Indeed, actually going all the way back to the Greek philosopher Hipparchus, comparing what he saw in the ancient times to modern star charts. His conclusion on the basis of this is that some stars seem to move independently of other ones, that not all stars are quote-unquote fixed stars as the ancients believed, that there are some bodies up there that move around, and even that seem to disappear for a while. Now, the phenomenon of comets has been known since classical antiquity, and in the time when Aristotle and others believed that the night sky was fixed, the appearance of a comet was generally regarded as an evil omen, and indeed even into relatively modern times, the appearance of comets has often been correlated, coincidentally of course, with the occurrence of plagues, the assassination of rulers, famines, and other disastrous events. So seeing a comet was often regarded as kind of a negative sign, this strange temporary star that shows up for a while and then vanishes. But Hawley thinks there might be a pattern. In 1705, he publishes a book called Synopsis Astronomiae Cometae, in which he introduces a new theory of comets, suggesting that they are bodies not like planets, in that they don't follow elliptical orbits, but rather that they have parabolic trajectories. Looking at comet data that he has collected over many centuries, well, from many centuries, Hawley observes that sightings of comets in similar parts of the sky occurred in the year 1456, the year 1531, the year 1607, and most recently during his own lifetime in 1682. He concludes that this is a 76-year cycle, and that the same comet is coming back again and again. The comet, of course, now bears Hawley's name, Hawley's Comet. You've all heard of it. It's probably the most famous comet in existence. Hawley predicts that if his pattern holds up, both his theory of cometary motion and his general mathematics behind it, that the comet named for him will show up again in 1758, and then again on 76-year cycles after that. Hawley does not live to see the reappearance of the comet that bears his name. He dies in 1742. But his comet shows up exactly as he predicted it did, not only demonstrating that his comet theory is correct, but also providing a very dramatic and definitive proof of Isaac Newton's models of gravitation and motion, because Hawley used the mathematics of those to predict the return of the comet. Hawley's Comet, incidentally, has made several appearances since that time. Showed up in 1835 and 1910. Famously, it appeared the year that the American author Mark Twain was born, and appeared again the year that he died. Twain said that he'd come in with the comet and he would go out with it, and he was absolutely right. Most recently, Halley's Comet showed up in 1986, and you can date me if you want by the fact that I can tell you that my granddad took me out in the backyard to look at it when I was a small boy. If you are keeping track, Halley's Comet is due to make its next appearance in 2061. So mark your calendars, it'll be a cool thing to see. Now, in addition to his work with comets, Halley also makes another very important and often forgotten contribution to astronomy. In the year 1716, he observes a rare event, a transit of the planet Venus across the face of the sun. He devises a triangulation method based on the astronomical phenomenon of parallax for using the sun, Venus, and the Earth to calculate how far away the sun actually is. Keep in mind that up till this point in time, nobody really had a good sense of how far away celestial bodies were. Most astronomers figured they were maybe a few thousand miles away at best. Well, Halley's math suggests that, okay, if his triangulation method is correct, then another transit of Venus will occur in the year 1761, and yet another one in 1769. He adds the precise dates that those things will happen. The prediction is kind of a radical one, because it suggests, if he is right, a very big universe. Again, Halley does not live to see his predictions come true, but the transits of Venus happen exactly when he said they did. And on the basis of his triangulation method, offers mathematical proof of a vastly larger universe than anyone imagined. Indeed, using Halley's formula, astronomers realize that the distance to the sun, rendered in modern terms, is approximately 153 million kilometers by Halley's math. Today we recognize it's about 149.6 million kilometers, but still pretty close. This is many, many orders of magnitude more than anyone had dared to imagine. And now astronomers are faced with the exciting and terrifying notion that the universe is monumentally larger than anybody had dreamed. And that, therefore, celestial bodies like the moon, the sun, the stars must be considerably larger than we thought they were. Shakes up astronomy in a very significant way. It's the first time anybody has applied actual empirical numbers to the size of planetary bodies, and by extension, for calculating things like the speed of their movement. Now, Halley becomes Astronomer Royal after the death of Flamsteed. You already heard about his somewhat sleazy contribution with Isaac Newton of facilitating the theft of Flamsteed's data and the publication of Historia Celestis Britannica. Even though they are called the Flamsteed numbers, Halley also devises the notation system that is still used to this day for recording the positions of stars. Couple little oddities about Edmund Halley that we must talk about before we leave him behind. For starters, it is believed that he was bisexual. It seems that he had affairs with not only the captain of the ship that took him to St. Helena for his astronomical research, but also the captain's wife. Halley came home on a different ship, needless to say. He also was a hollow earther. Halley was a big advocate of hollow earth theory, which we talked about a little bit last week. He actually offered the idea that there was not one, but 7 Earths, one nested inside the other, each one with its own stars, planets, and sun within it, and with its own people and flora and fauna. Where he came to that conclusion, can't begin to tell you. He made an attempt to calculate the size of an atom. His math was very much off, but it was an interesting exercise in statistics nonetheless. But I think the most interesting story about Edmund Halley is a mystery concerning him. In the year 1698, Edmund Halley was appointed by the British Crown to undertake a voyage to map the Earth's magnetic fields. Okay, reasonable thing to do. We know the Earth has a magnetic field at this point in time. Mapping it out would be quite useful for scientific purposes. To that end, Halley is given the command of a British naval vessel called the Paramour. It is actually the only time in the entire history of the British Navy that a civilian has been given the captaincy of a naval ship. Hawley sets out on the Paramour to map out the magnetic fields, goes into the Atlantic, goes into the Mediterranean, puts ashore for a while in the Mediterranean, and spends several months traveling in France, Italy, Germany, and Austria. Okay, do a little bit of touring while you're there, take some magnetic readings on land. Sounds like a reasonable thing to do. During his time in France and Austria, he actually acts officially as a royal envoy, delivering message and news and picking up documents from the British monarch and to the British monarchy. So, kind of a prominent spot. He does more than one thing with this trip. Here comes the mystery. Edmund Hawley's voyage, we have since learned, was a little bit more than it looked like. You might think, why exactly is my astronomer mapping the magnetic fields but also serving as a royal envoy? And why did we have to give him the captaincy of a naval vessel to do that thing? We have since learned that Edmund Hawley's trip on the Paramour was financed out of the British Crown's black budgets. And if you don't know that term, that was the money that was set aside in the Elizabethan era for use for secret missions and espionage. Hawley was a spy, and he was being sent to spy on France and Austria. What was the nature of the mission? Here's the best part of the story. Under British law, it is required that classified files be opened after 75 years from the date of the events detailed within them. There's actually that recently a whole bunch of World War II files have been opened up, and among other things, we've learned that the famous chef Julia Child was actually a British spy during World War II. Nobody knew that. But here's the thing. They can be kept sealed if, for whatever reason, the content of those files is still considered a matter of British national security in the present day. As of last year, British intelligence refused to open the files from Hawley's voyage. Which means I leave you with the thought that whatever Edmund Hawley was doing in France and Austria in 1698, considering that the government of France isn't even the same government then as it was now, and Austria isn't even the same country today as it was then, whatever Hawley was doing in 1698 in those nations is something that, as far as the British intelligence services are concerned, is still relevant enough to British national security today that it needs to remain classified more than 300 years later. I am one of many science historians who would happily give a non-trivial finger to find out what is in that file. All right, folks. So on that particular mystery, I think this is a good time to leave off our lesson. Next time we get together, we're going to talk about other Enlightenment science. We're going to look at the development of chemistry. We're going to look at the study of electricity, maybe hit an astronomer or two, and we're going to find out about science being done in a place called America for the first time. Thank you for your attention. I'll talk to you all soon. Good night.